Welcome to the deep dive. Today we're zeroing in on a core area for anyone tackling senior software engineer technical interviews. The ins and outs of data replication in distributed systems, particularly the challenges that pop up when read requests are served by asynchronous followers. We're going to unpack why this matters, explore the potential pitfalls, and dissect the consistency models designed to address them. Think of this as, your shortcut to confidently navigating these crucial system design concepts.
Exactly. When you're in that interview setting, they're not just looking for whether you know what replication is, but whether you understand why it's essential and the trade-offs involved.
Right.
Beyond just providing resilience against server failures, replication is fundamental for building systems that can handle massive read traffic. Think about the sheer number of times information is read versus written on most web applications. It's also key to reducing latency for users who might be geographically distant from the primary data source.
Right. That ability to scale reads using read replicas or followers is incredibly attractive, especially for those read-heavy workloads we see all over the web. But here's a critical point for that interview discussion. To achieve that scalability and high availability, ensuring the system stays up, even if individual components fail, we often have to lean on asynchronous replication. The primary server, the leader, handles the writes, and then those changes are propagated to the followers.
And that asynchronicity is where things get interesting from a consistency perspective. While it's often a necessary compromise for scale and availability, synchronous replication can become a bottleneck and a point of failure. As you add more replicas, it inherently introduces the possibility that a user might read outdated information from a follower that hasn't yet caught up with the leader.
Okay, so let's dig into what happens when those followers lag behind. We're talking about replication lag, right? That delay between a write hitting the leader and that change being reflected on a follower. Now, in an ideal world, this lag would be, well, imperceptible.
Ideally, yes. Sometimes it is, maybe just a few milliseconds.
Yeah.
But the reality, especially under heavy load or if there are network hiccups, is that this lag can become significant seconds, even minutes.
Wow, minutes.
Yeah. When that happens, the potential for inconsistencies becomes a very real and practical concern for the applications relying on that replicated data. This isn't just a theoretical edge case. It can directly impact the user experience.
Let's illustrate this with a scenario you might encounter or even be asked about in an interview. Imagine a user submits a comment on a blog post and then immediately refreshes the page, expecting to see their witty remark. If their read request happens to hit a follower that hasn't received that latest write from the leader yet,
the comment will be missing, vanished. From the user's perspective, it's as if their action didn't register. This is a prime example of read after write inconsistency. In an e-commerce context, imagine a user places an order and doesn't see it in their order history immediately after. That lack of immediate feedback can lead to confusion, frustration, and even the user thinking the transaction failed.
Exactly. It undermines the user's confidence in the system. So the question then becomes, how do we provide a better experience? How do we ensure that users generally see their own updates, even when we're using asynchronous followers for read scalability? That's where read after write consistency comes into play.
Right. Read after write consistency, often referred to as read your writes consistency, guarantees that after a user performs a write operation, any subsequent read operations they perform will reflect that write. It's a crucial guarantee for maintaining a coherent user experience.
Okay.
There are several strategies to achieve this. One common approach is to intelligently route read requests. For data that the current user has recently modified, you can direct those reads to the leader.
So if a user updates their profile information, the subsequent read of their own profile would be routed directly to the leader, ensuring they see their changes. This makes perfect sense for data that's highly specific and likely to be modified by the user viewing it. However, in an application where a large percentage of data is user-generated and could be modified frequently, like social media posts, always reading from the leader could put undue strain on it, negating the benefits of having read replicas in the first place.
Precisely. That strategy doesn't scale everywhere. In those scenarios, you might employ other techniques. One is to keep track of the time of a user's last write. For a short window after they make a change, say 30 seconds or maybe a minute, all their read requests could be directed to the leader, giving the followers some time to catch up.
Like a grace period.
Yeah, sort of.
Yeah.
Another option is to monitor the replication lag on your followers. You could then avoid serving reads to a user from any follower that has a significant lag, say more than that 1-minute threshold we just mentioned.
That sounds like a more dynamic approach, adapting to the current state of the replication process. What about involving the client in this? Can the browser or app help?
Yes, the client can also contribute to maintaining read-after-write consistency. For example, when a client makes a write, it can record a timestamp of that operation. Then, with subsequent read requests, it can include this timestamp.
Okay.
The system can then ensure that the replica serving the read has processed all writes up to at least that timestamp. This could involve using logical timestamps, which track the order of events, or relying on system clock timestamps, although the latter brings in the complexities of clock synchronization across distributed servers. That's a whole other can of worms.
Right, clock skew. And as we touched on earlier, the complexity ramps up when you're dealing with multi-data center deployments, doesn't it?
Absolutely. If you need to route a read to the leader to guarantee read-after-write consistency, you need to ensure that request is directed to the right data center hosting the current leader.
Ah, right. Geographic routing.
Furthermore, consider the cross-device scenario. A user might save a document on their laptop and then immediately open the same document on their tablet. They would expect to see the saved changes naturally.
Yeah, definitely.
Achieving this kind of cross-device read-after-write consistency typically requires some form of centralized metadata management to track the latest state of a user's data across all their devices.
So we've covered ensuring a user sees their own rights. Now let's think about what happens when a user makes a series of reads. What kind of inconsistencies can arise there?
One particularly confusing issue is a violation of monotonic reads. Imagine a user viewing a list of comments. They see a new comment appear at the top. They refresh the page, maybe just hitting F5, and suddenly that comment is gone.
Whoa.
This isn't a case of not seeing their own right. It's seeing something and then seeing it disappear on a subsequent identical read request.
That would be incredibly jarring. It would feel like the data is fluctuating randomly, like time is going backward. Why does this happen?
This can occur if the user's different read requests are routed to different followers that have varying levels of replication lag. The first read might hit a follower that has already processed the new comment, while the second read might go to a follower that is still behind and hasn't received it yet.
So from the user's perspective, it looks like time is moving backward. They saw a more recent state, and then a subsequent read shows an older state. Very confusing.
Exactly. Monotonic reads is a consistency guarantee that addresses this. It ensures that once a user has observed data at a certain point in time, any subsequent reads they perform will show data at the same point or a more recent point in time. They won't see an older version of the data.
Okay, so it stops things from going backward in time, visually?
Pretty much. It's a stronger guarantee than eventual consistency, but not as strong as full strong consistency.
How do we implement monotonic reads? How do we make sure a user's view of data doesn't regress like that?
A common technique is to ensure that all read requests from a specific user are consistently directed to the same replica. You could achieve this by using a hash of the user ID to determine which follower serves their reads.
Sticky sessions, but for replicas.
Kind of, yeah. As long as that follower remains available and is progressing in its replication, the user will maintain a consistent, non-decreasing view of the data. Of course, you need to have a strategy for what happens if that particular replica fails.
Right, failover.
In that case, subsequent reads would need to be rerouted to another replica in a way that ideally preserves the monotonic guarantee, perhaps by choosing a follower that is known to be at least as up-to-date.
Okay, so we've looked at a single user's rights and a single user's sequence of reads. Now let's consider how multiple users might observe a series of related events. This brings us to the concept of consistent prefix reads, which I think is best explained with a classic example.
Ah, yes, the question and answer example. Imagine a scenario where one user, let's call her Alice, posts a question. What's the capital of France? Shortly after, another user, Bob, replies. It's Paris. These two actions are causally linked. Bob's answer is a direct response to Alice's question.
That's a clear sequence of events, question, then answer. Seems straightforward.
Now, imagine a third user, Carol, is viewing these posts through a system with asynchronous followers. If the follower that handles Alice's posts has a significant replication lag, while the follower handling Bob's responses is very close to real time, what might Carol see?
Oh no. Carol might see Bob's answer, it's Paris, appear before she sees Alice's question, what's the capital of France? That would be incredibly confusing. It violates the natural cause and effect.
Exactly. This is a violation of causality, and it's what consistent prefix reads aims to prevent. The guarantee of consistent prefix reads ensures that if a series of writes are causally related and happen in a specific order, anyone reading those writes will see them in that same order. They won't see a later event before an earlier event that caused it.
And you mentioned earlier that this is a particular concern in systems that are partitioned or sharded. Why is that? Why does sharding make this worse?
In a database that's not partitioned, writes are generally processed and replicated in a more or less global order.
Mm,
However, in sharded systems, the database is broken down into multiple independent partitions, each often with its own leader and followers.
right.
Writes within one partition are ordered, but there's no inherent global ordering across all partitions. So if Alice's question goes to one partition and Bob's answer goes to another, and if the replicas for those partitions have different replication lags, a reader querying data that spans both partitions could easily see the answer before the question.
Ah, because the partitions are replicating independently.
Precisely. No coordination on the global order of writes across partitions, generally speaking.
So how do we address this? How do we ensure that these causally linked events are observed in the correct order, especially with sharding?
One approach is to try and ensure that writes that are causally related to each other are routed to the same database partition. In our example, you might try to keep Alice's question and Bob's answer on the same shard.
Co-locate related data.
Right. However, this isn't always feasible or efficient, especially in complex applications with intricate relationships between data. It can lead to hotspots on certain partitions.
True.
There are also more advanced techniques that involve tracking the causal dependencies between different writes, allowing the system to delay the visibility of certain writes until their causal predecessors have been observed. These often involve mechanisms for establishing a partial ordering of events across the distributed system, like using vector clocks or similar concepts.
This really underscores the complexity of building reliable systems with eventual consistency. You can't just assume that data will always make sense to the user. You have to be very deliberate about the consistency guarantees you can offer and how you achieve them.
Absolutely. And while application-level solutions can be implemented to provide stronger consistency like the routing tricks we discussed, they add complexity and can be error-prone. If you mess up the logic, you're back to inconsistent states. Ideally, the underlying data storage system would offer more robust consistency guarantees out of the box.
Which leads us nicely to the concept of transactions. We often think of transactions as a way to maintain consistency within a single database node, like ACD guarantees. How do distributed transactions factor into this discussion about replication and consistency in distributed systems?
Right. Distributed transactions are designed to provide strong consistency across multiple nodes, potentially across different partitions or even different databases. They aim to ensure that a set of operations, even if they involve different servers or partitions, are treated as a single atomic unit. Either all the operations succeed and their changes are made visible consistently across the system, or none of them do, leaving the system in a consistent state.
All or nothing, but across the whole system.
Exactly. This can greatly simplify application development by pushing the responsibility for maintaining consistency down to the database level. The application developer doesn't need to worry so much about partial failures or intermediate states. However, distributed transactions are notoriously complex to implement efficiently and can come with significant performance and availability trade-offs, which is why many large-scale distributed systems initially opted for weaker, eventual consistency models instead. It's a classic trade-off.
So we've taken a deep dive into why replication is essential for building scalable and available systems, but we've also highlighted the significant challenges that arise with asynchronous replication, leading to potential issues like read after write inconsistencies, violations of monotonic reads, and those confusing scenarios caused by a lack of consistent prefix reads. We've also touched on some of the strategies used to mitigate these problems and the role of more robust consistency mechanisms like distributed transactions.
Exactly. Understanding these different consistency models, read after write, monotonic reads, and consistent prefix reads, and the specific problems they are designed to solve is a critical aspect of understanding distributed systems. Being able to articulate these concepts clearly is invaluable, especially when discussing system design in a technical interview context.
And for those of you preparing for senior software engineering interviews, being able to explain these trade-offs, describe the scenarios where these inconsistencies can manifest, and discuss potential solutions demonstrates a strong foundational knowledge of distributed system design principles. It shows you're thinking about the real-world implications of architectural choices, not just the textbook definitions.
As you continue your interview preparation, think about the various applications you use daily. Can you identify scenarios where you might have encountered these types of consistency issues? Like, have you ever refreshed a page and seen something disappear or posted something and not seen it right away? Considering how those applications might be designed to handle them can really solidify your understanding.
Yeah, apply it to the real world. And finally, a thought to consider as you continue your learning. As distributed systems become even more prevalent and the demands for real-time data processing increase, how will the balance between availability, consistency, and performance continue to shift? What new challenges might emerge in ensuring a consistently coherent and reliable user experience in this ever-evolving landscape of distributed computing?
That's a great question to ponder. The goalposts are always moving.
Thanks for joining us for this deep dive.